Good morning. All right, for this warm-up here, since you are just watching the video, you're trying to convince the amount of petals that this polar graph will have. Then you'll try to sketch what the polar graph looks like. So let's take a look at the two that are given. R equals cosine 3 theta, R equals cosine 4 theta. So if you remember from last class, we talked about if there's an odd or an even number for a frequency, that will tell you how many petals this graph has. So looking at the one on the left-hand side, because this is an odd value, we're going to have 3 petals. The one on the right, because it's even, we're going to have double that amount. We're going to have 8 petals. So if we were to go ahead and sketch this, please make sure that you understand when you start sketching it, right, on a polar graph, that first point there at 0 degrees is at a radius of 1. So it is going to be starting over here. And then it will be looping around. Okay, for today's objective, we're going to be learning how to sketch a different type of polar graph called a Limacon curve. And then we're going to be starting just a little bit of finding slope of polar functions. Okay, so let's review again about this one. R equals cosine theta. What kind of polar graph is this going to look like? Well, since the amplitude is 1, we know this is going to be a circle here, specifically right on at 0 degrees. It's going to be at 1. That's going to be my diameter. It'll look something like that. This is specifically what it looks like from Desmos here. All right, what if now I add a shifting to this circle, 0.5 plus cosine theta, or if I put a 2 in front of there? What do you think it would look like? I want you to just take a second and think about it, then come back and we'll discuss. All right, so the one on the left is the 0.5 plus cosine theta. So I would sketch a little bit in your notes on that one. And then the one on the right is 2 plus cosine theta. So everyone should see a little difference there. We have a little circle going inside the circle there. This one's more looking like a circle on the right. Well, why is this happening? Why are they different? So let's take a look at their actual XY graph. So here, because this little piece is going below the x-axis negative, and if I was to figure out the actual angle there, it is actually going back inside this area here and making that circle. The one on the right-hand side, because it's 2 plus, because it's shifted up 2 on an XY graph, right? These are all high above the x-axis, so it is stretching it more to make it almost a circle. Okay, so let's take a look at now if I have 2 plus, but now my amplitude in front is 2 cosine x. So here is your XY graph for 2 plus 2 cosine x. So that means that it is an amplitude of 2. It was shifted up 2, so this is my midline, right? So the amplitude here is up 2, right, and then down 2. So that's what it's showing us here. And then on the right-hand side, it's showing us the graph. So here's what this Limacon curve looks like. It doesn't have a whole little circle on the inside like the 0.5 one from the previous page. So let's discuss why this is like this. So definitely sketch these two down. If you have colors, we're going to do what's coming up next in the next couple of slides. So let's take a look. All right, so at 0 degrees, my amplitude, my angle is 4. So at 0 degrees, we are starting right here at 4. At pi over 2, my answer is 2. So at pi over 2, which is right here, here's my radius, pi over 2. So this whole area you should be shading in, whatever color you have. This is my blue. This is all above there on the polar graph. Then it's switching from pi over 2 to pi. Here's that piece that's making that little piece coming out like this. in green, at pi degrees, it goes back to 0, the radius of 0. So this is green here. Then, after that, it's going from pi over pi to 3 pi over 2, so from 180 to 270. So at 270, right, it's again a radius of 2. And that's down here, 2 comma 3 pi over 2. And then it connects all around from back to 2 pi 360, which is a radius of 4 again. So that's what's happening there for this Limacon curve when it's 2 plus 2 cosine theta. Okay, so we had something like this. So this is the one we just did on the left side. How do you think the one on the right side is going to differ? So we had an example like this just before, a couple of slides back, where it dipped below the x-axis here. So what's going to happen to the Limacon curve is going to be making that circle on the inside. So let's take a look. So definitely sketch this one. Here it is. This is called 2 because it is shifted up 2. So take a look. Up 2 plus 3 cosine theta, cosine x, cosine theta. So my midline for this one is at 2, right? So it's starting up here at specifically 5 here. Ending at 5. Is going down here to -1. So let's see what's happening here with this color. So at 0 degrees, my radius is 5. So this is what it's showing us here being plotted. Then specifically at pi over 2, my radius is 2, which is plotted here. So it's making that big circle going out. Then it's coming back in between pi over 2 and pi. It's going down at pi. The radius is -1. So remember from polar graphs, here is your pi degrees, but because the radius is negative, that's why I'm going backwards on the line and plotting it here. And then it's going to make that circle inside and then come back out. And then make the rest of it. All right, how about this one? Here, this XY graph is shifted a little bit more up here, okay? It's shifted up by 2 because this is looking like this is the midline here at 2. So this is a y equals cosine x plus 2. What do you think this will look like? We had this also before, so it's a good idea to have this one copied. Looking like it's making almost a circle shape there. Okay, so let's go ahead and try to plot this one. At 0 degrees, it's 3. Here it is. Comes around. At pi, it's actually 1. So it's coming more on the outside here. It's not going to the origin, right? Because it's not passing the x-axis here. And then again, at 2 pi degrees, it's going back over again to where we were for a radius of 3. So for these types of Limacon graphs, you have to understand what's going on in the XY graph, the shifting wise, above the x-axis, below the x-axis there. All right, for this last little graph here, what do you think this will look like as a polar graph? So this one, again, is thinking it is above the x-axis. We have a frequency that looks like it's 1, 2, 3, 4. So we're considering petals maybe, right? But it is above the x-axis. Is it more circular? A higher frequency means that the graph likely won't be circular. It could take on maybe another shape of a graph. It's never crossing the x-axis here or the 0, right? So that means it's not going to cross through the origin to make a Limacon curve there. So if we were to actually do this on Desmos, this is what it would look like. So here are some important notes if you'd like to copy that I just said. It's looking like this. So it's not having double the amount of petals here. It's looking almost like it's just having 4 here. So this is different than yesterday's lesson because of the shifting up above the x-axis here. For this graph, we know it's a sine one, the frequency is 4, but it's shifted up by 2 here, right? All right, so my bad. I was looking at another picture in my mind. This is actually shifted up 1.5, right? There's the new midline. So this should say sine 4 theta plus 1.5 here. Okay, so the next one that I thought about is this one here. So take a look. If you zoom in here, again, let's take a look. We have a high frequency. It's never 0 here. 1, 2, 3, 4. It is a sine wave, so it's sine 4 theta. And then here, this one is definitely plus 2 here, like I thought from the previous one, because the midline is at 2 here. And this is kind of what it would look like. So it's more pulled out, that pedal thing. It's not touching that origin that we were used to from yesterday's class. Okay, so what is the frequency doing here? What is the midline doing? So the midline is telling us that it's not going to be touching the origin here, right? And this frequency is telling us how many of these kind of looks like petals that it will have. But it's not going in like we had from yesterday's class for those rose petals. All right, so that is all about Limacon curves, different than the petals, rose petals from yesterday. Now we're going to get into tangent lines, specifically for polar graphs, polar functions. So make your title as Constructing Tangent Lines. We're going to start with just a regular line, y equals x squared. We know an equation of a line, this is in point slope form, is y minus y1 equals m times x minus x1. Okay, and to make tangent lines, we are going to be finding the derivative of x squared using the power rule. You could do this on Desmos if you like on the next slide. You don't have to here, but let's just kind of walk through it here. So we want in general terms what the equation of this tangent line would be. So here is my derivative, y prime of x squared is 2x. I'm going to designate my y1 as the original equation. I'm just replacing it with a. This is if we were doing it on Desmos, so this would be, instead of x squared, it'd be a squared. I'm going to designate my x just as a. And then my slope, which is my tangent line, is the equation that we just figured out, but just replacing the x with a. So I'm taking these three amounts, and I'm plugging it in the equation that we know as this. And this is what we're getting. So this is the equation of the tangent line, specifically for x squared. All right, let's try now this one. Y equals x cubed. You could pause the video and see what it would be. What would be the equation of this tangent line, specifically at x equals a. So let's go ahead. We have our power rule, our derivative, 3x squared. We're making the original equation a to the third instead of x to the third. We have our x as a. We found our slope, which is our tangent, right? 3a squared. And now we're going to organize it. So it's going to say y minus a cubed equals 3a squared x minus a. And there it is. All right. Now, let's start to look at polar graphs. So we'll start off with this one here. Constructing a line tangent to the graph of r equals 7 at a random x equals a. All right, so let's talk about this. If I was to graph this, this would be a circle, correct? So what were the two values to make a circle? It was cosine and sine, but because this is 7, we know that one of them is going to be 7 cosine theta, and the other one is going to be 7 sine theta. Which was x and which was y? The x was the cosine one, the y was the sine one. So it's the same concept as before. To find the slope, to find the tangent line, we have to do the derivative. So we need to get the derivative of this x equation, and we need to get the derivative of this y equation. All right, what is the derivative for cosine? That is negative sine. and we're bringing down the 7. So negative 7 sine theta. What's the derivative for sine? Is cosine. And also bringing down the 7, so 7 cosine theta. And now we need to divide dy over dx. So I'm doing 7 cosine theta, all divided by negative sine theta. Looking like those are going to cancel the 7s, right? And now specifically, I could actually reduce this a little bit more. What is cosine over sine from tangent? That's the reciprocal of tangent. And what was the name of that one? Cotangent. Negative cotangent theta. Okay, so just like before, we designated, before it was x, here we have theta. So we're going to be changing this to my x equation, and my y equation with a in it. So this x equation here is going to be 7 cosine a, and this y equation is going to be 7 sine a. And now here's my equation of the tangent line. And we know this is my m. We're going to make it negative cotangent a. And now we plug everything in. So we have y minus 7 sine a to equal my slope, which is negative cotangent a, times x minus 7 cosine a. Okay, so we're going to be getting into more of these when during next class, but these are the basic ones for polar graphs. Just knowing how to get the derivatives for each, dividing dy over dx to get the equation of a general tangent line. And these next couple of slides go through what I just did, and you could look at the slides also there. Okay, so after you have done this, make sure you've submitted the copy of your notes online in Google Classroom so that I know that you watched it and you took some notes.